So I guess for me, mathematics was really just always around. I was always exposed to mathematics as a kid. So I was always interested in sciences. That was clear. But it wasn't clear whether I wanted to study in mathematics or physics or computer science. My dad was also a mathematician, and so that's why we traveled around. So the reason why I was actually born in Geneva was because he had a postdoc position in Geneva at the time, and then went back to Austria on a kind of assistant professor position, and then moved to position in Heidelberg, and then back to primary school, high school, and university studies in Geneva. One of my primary school teachers also sort of tried to challenge me a bit, and so he would give, additional problems that were not at that kind of level in a way, and that I found sort of amusing or interesting. And also, of course, I would ask my dad what he was doing, and so he would try to explain things to me. So in some sense, he was trying to explain to me what a differential equation is when I was, 11 or 12 or something. Of course, in some, intuitive, maybe pictorial kind of way, not in a formal way. But so I think that helped a lot, because I had some sort of more of an intuitive grasp of mathematics when I grew up as a kid, and not, it's different from when you get exposed to it at school, and it's very dry and formal somehow, right? And that turns many people off. So in high school, away from the school period, I was really more into coding. So I was actually writing software as a, out of school hobby, if you want. Like my extracurricular activity was actually mostly programming, which of course is very close to mathematics as well. So I picked up some kind of notions of signal processing and sound analysis in that way. And then I also used that for school projects. So I remember when I was in, maybe it wasn't the last year, it was the second to last year of high school, we were supposed to do biology projects. And so the project that I chose was to make sound recordings of the frogs. So there was a pond in front of the high school, and there were frogs in that pond. And so I made sound recordings of those frogs. And then the biology teacher had an audio tape which had recordings of many different species of frogs. And so then I wrote a sonogram functionality, which is essentially you take pieces of Fourier transform on time slices, and so you see the different frequencies, how they evolve over time. It gives you a graphical representation of your sound, that you can kind of see your sound if you want. And then I used that to compare the recordings of the frogs that I made in the ponds to the recordings on that audio tape. And it worked pretty well. So you could see that it was one of those species of frogs, so you could recognize the species, but you could also see that they were actually different. So they were kind of speaking in a slightly different dialect than the frogs on the recording that we had. So that was kind of fun. I chose to study physics and not mathematics, in part in order not to do the exact same thing as my father. And also he was teaching at Geneva University. So I thought it would be slightly awkward to follow his lectures. But then on the other hand, it turned out you couldn't escape it, because he was teaching the first year analysis class, which was taken by mathematicians, physicists, and computer scientists. So whatever, any of the topics that I was interested in, if I studied it, I would have had to take his class anyway. But yeah, originally that certainly played a role in the decision to study physics rather than math. I was never that good at experiments in physics, but I liked physics. So I liked to somehow understand how nature works and understand how to make predictions and how to model physical systems. But I wasn't that good at actually, myself setting up an actual experiment and do measurements on it. So that wasn't an aspect that I enjoyed that much or was that good at. And so that's why then during my studies I was much more on the theoretical side of physics and then kind of moved much more and more towards mathematics. Right, so I did my PhD in physics, but, on paper it was a physics PhD. But I think in pretty much any other university it would have been considered a mathematics PhD, right? It was really a mathematics PhD, it just happened to be in the physics department. And so it was very natural then to, after my PhD, to go to a mathematics department and not to a physics department. So that's why I went, after PhD, I went to the University of Warwick, partly because, well, it was one of the strong places in the UK for probability theory, which is my area of mathematics. And of course, one reason why I chose to go to the UK was because by that time I had met Xiumei, who's now my wife, and she had a position in the UK at the time. So my area of research is stochastic partial differential equations. So they are equations that describe systems that are spatially extended, so they depend on location in space and they also evolve in time under some random influence. So I guess the simplest example you can think of is if you stir a cup of coffee, right? So you have a cup of coffee, now you want to describe, for example, the milk that gets stirred in your cup of coffee, so you put the milk in, and now your milk it depends on space, right? So you put the milk into your coffee, so there's some places where there's milk, there's some places where there's no milk, some places where there's a little bit of milk, so somehow the concentration of milk is different in different points in space. And then, of course, it changes over time. You see the milk move around, so it depends on time. And now if you stir it, well, you essentially stir it around in some random way, right? So there is some random force that acts on this milk that makes it move around in some random way, but it still evolves according to the equations of, the Navier-Stokes equations, which is the equations of fluid motion that people know since the 19th century. And so that's the type of systems that I work on, yeah. So one of my interests is how systems change under changes of scale. And that's very often, you have a description of a system which is given at some microscopic level, and you might have different systems that behave in similar ways that have very different microscopic descriptions, right? So it's a phenomenon that physicists call universality, which says that you should really, in some sense, you have classes of systems that have similar or the same macroscopic behavior, even though they have very different microscopic behaviors. And now you want to understand how comes, a given microscopic description falls into one class or in another. Like mathematically, how, can you actually prove that two systems with very different description behave in a similar way when you look at them at very large scales, right? So that's something which is still not very well understood. So it's in some sense, from a physicist's perspective, it's quite well understood. But it's a somewhat phenomenological understanding. From a mathematically rigorous perspective, it's still not very well understood, actually. For example, you can observe that you take a flame front that propagates. So for example, if you have say maybe not a forest fire, but something like a fire that spreads in the savannah, right? So So you have this dry grass that kind of burns, right? And you have this flame front that moves. And it's so in this dry grass that burns, the flame front is usually very well defined. So you really see there's a very narrow part of grass, because grass burns very fast, right? So there's a very narrow bit of grass that is burning at any one time. And then you have the black part that was burnt on one side and the brown part that is not yet burned on the other side. And then you want to describe, how this moves. And it turns out that this is really, it behaves in the same way as many other systems of the same type. Right? So you can do lab experiments with liquid crystals, which in principle, the microscopic description of the liquid crystal has nothing to do with, grass that burns in the savannah. But you can see that they actually have the same behavior, and it's in a very sort of quantitative way. So it's not just qualitatively. In both cases, you somehow see a front, and the front moves, and it somehow fluctuates. There's some randomness, right? So your flame front is not going to be completely uniform. It's going to be random. It's going to fluctuate, and you want to describe these fluctuations. And it's really the quantitative description of these fluctuations, which is the same for burning grass in the savannah and a liquid crystal that undergoes kind of a phase transition. And so that's something one can observe, and one can use that to make some predictions. But what we're interested as mathematicians is more understanding why, like what is the mathematical mechanism that is underlying this phenomenon. Right? So one thing that drew me towards mathematics was the fact that in mathematics you have a kind of absolute understanding of something. Right? So you kind of you can really justify every single step. So when you do a mathematical proof, if the proof is correct, you have really justified, in some sense, you have answered every single objection that someone could possibly have come up with. And furthermore, you have convinced your audience about the fact that there cannot possibly be any objection, right, that wouldn't have been answered by your argument already. So it's not just objections that you received. You have to show that there cannot be any objection anymore somehow, right? And so you have to cover your bases in a completely exhaustive way, which is somehow different from, say, theoretical physics, where you have to make a very convincing argument, right? But it's not, a convincing argument is not an absolute proof of something. And so I was always, when I was studying physics, I was always somewhat worried that, I would get carried away, make something that sounds like a convincing argument, but then, somebody would come 2 years later and say, well, no, but this is all completely wrong. And so I felt like I wanted to, have some understanding where you couldn't possibly come back and say, well, but actually this argument really doesn't quite stand up to scrutiny if you think about this and that you hadn't thought of, right? In the mind of somehow the general public, mathematics, right? If you talk about do the math, you're really usually talking about numbers, right? You're very often talking about statistics in some sense, or just, splitting the bills or figuring out interest rates or that kind of things. And as mathematicians, usually, so numbers is essentially arithmetic, but, learning how to calculate, it's a bit like learning how to spell, right? Just learning how to spell words has essentially nothing to do with being a good writer, right? you can be a good writer and not know how to spell words, because if you don't know how to spell them, there's a spell check anyway that's going to spell them for you, right? And just because you know how to spell words has absolutely no influence on whether you can write or not, right? And so it's the same for mathematics. And so, I mean, I guess most writers are good at spelling just because they read a lot and they see the words very often. And so in the same way, most mathematicians are actually reasonably good at calculating. But, you know, being good at splitting the bills in the restaurant is completely unrelated, if you want, as to being a mathematician, in the same way as being able to spell words is completely unrelated to being a writer. You know, when you finish your studies and you don't really know what to expect in some sense. And so at the time, I didn't really, even though I had just finished my PhD, and so I knew about research level mathematics, of course, and so I knew in some sense what it is to be a mathematician. But I didn't really have a very good assessment of my own abilities. I didn't really have a good reference somehow. And so I had no idea about, you know, whether I could be a good mathematician or not, and whether, you know, I would be able to get a, you know, position in some decent university. And so, yes, I had that plan B that I would go and do a postdoc. So I received this fellowship from the Swiss Science Foundation that allowed me to go to Warwick for a couple of years. And so the Swiss Science Foundation has these fellowships where they pay you for 2 years to go to some other country as a postdoc, essentially. And so I had that. And so I thought, okay, so I try it for 2 years, I see how it goes. But if it doesn't work out, or at least if I feel like it's not really going anywhere, well, then I can always be a software developer, because I had that experience as well. And so that's something I probably would have done full time if it hadn't worked out. But I mean, I think it's sort of, I mean, different people have different attitudes, but I mean, personally, I'm maybe somewhat risk averse. And so it was useful for me to have that plan B in order to, I guess it gives you a certain freedom, because it means that you have less pressure to actually, you know, succeed in getting some position. I mean, some people know exactly what they want to do, and they have this sort of, you know, vision for themselves, that, you know, they have this sort of straight path that's going to go into their future, and they stick to it. I mean, that wasn't really my case in a way, but that's a very personal thing, right? So it's like everybody has to figure that out for themselves. I don't think one can kind of, you know, give kind of general advice. I did continue somehow developing that sound editor that I started off as a school kid, the one I used for this biology project. And at some point, when I was around the time when I was finishing my PhD and when I was moving to Warwick, it became useful enough so that, you know, you could actually distribute it and people would be paying to use it. So it was somehow more or less a sellable product. But I never really turned it into a real business, if you want. Right? So it was always more of a hobby that I worked on in my spare time, and I tried to maintain it and try to make sure that it, you know, remained usable and somewhat modern and useful to people. Universities use it as a teaching tool as well. So it's also used by musicians or journalists for podcasts, audio journalists typically, or video game producers or bands, and, you know, there are lots of different type of people. People also use it as a teaching tool, because there's visualization tools, so you can kind of get some kind of intuition of how sounds work in a way. Yeah, I always somehow liked listening to music. I enjoyed listening to music. And so I enjoyed sort of tinkering with sound. And then at the time, in the early 90s, there were not that many tools available on the computer. So on the Mac, I remember there was a software called SoundEdit, which I was using at the time. But it, was somewhat limited in what it could do. And so it was just, you had no choice in some sense. If you wanted to do something else, you just had to write your own software from scratch. I mean, in the early 90s, there was not so much software around. It wasn't that developed. And so, so that's what you did. Music is the most abstract of art forms in some sense. And I guess mathematics is also a type of abstract art form, probably even more abstract than music. So I guess many mathematicians have some affinity with music. And it's also maybe structured in a more mathematical way. So, there are a number of mathematical principles that can be found in musical compositions. So in that sense also, it's a very abstract art form which is at the same time structured in a certain way. So I guess that's what makes many mathematicians sort of feel close to music in a certain way. Yes, I guess every mathematician has some years or months where you try to think of something, you try to prove something and somehow it doesn't work, or you've thought you had a path towards a proof and it's all almost written up, but then you realize that there was actually a mistake and some part of it collapses, and then hopefully you can still keep the rest and kind of rebuild the part that collapsed in a way that makes it work. But in some sense, it's more dramatic when you're young, because when you're doing your PhD or you're a young researcher shortly after your PhD, you typically have one problem that you're thinking about, or maybe two problems that you have in your head that you think about. And then it might be that for 3 months you have no idea of what you're supposed to do. Your PhD advisor gave you this problem. Of course, your PhD advisor doesn't tell you how to solve it, because maybe they themselves don't know, or maybe they have some idea, but it's not clear that the idea is correct. And then you can really get stuck, and that's part of learning to be a researcher, I guess. But then as you advance in your career, of course you have more and more projects in parallel with various people. And so in some sense, if you're stuck on one or two of these projects, well, you always have other projects that you're working on at the same time. So in that sense, you're never really stuck on all fronts simultaneously, because you have sufficiently many of them going on in parallel. I mean, sometimes you just have an idea that kind of pops in your head and you don't really know where it comes from, but it comes from the fact that you have the problem in your head, right? So you have, once you have a good enough understanding of a problem, you sort of interiorize it, and then maybe even if you don't think about it consciously, it somehow stays somewhere in the back of your head. And then sometimes, your subconscious sort of sends you some signals. And then maybe you have some idea about something that you could try. And, maybe it doesn't work, but maybe something works. Or more often than not, you see, what you end up doing very often is that, and that's what everybody does, right? Is you try there's some dream problem that you would want to solve, so some big unsolved problem. Of course, you know either you're never going to solve it, or you just have no idea how you would possibly approach it. And so then you try to find maybe some particular aspect of that big problem that feels to you like, well, it encapsulates one difficulty of that big problem, but it sort of tries to isolate it, right? So you try to find a simpler problem which sort of extracts one particular difficulty of the big problem in a way that, sort of simple enough so that it feels less intimidating and you can imagine that you might be able to know how to go about it, right? But it's still sufficiently interesting that you think that if you manage to at least solve that simple problem, that's still something that, people would be interested in and where you would actually learn something from it, right? You cannot just somehow decide, here I'm going to pick this famous unsolved problem off a shelf, and today I'm going to start thinking about how to solve this big famous unsolved problem. And then if I haven't managed to solve it within 6 months, then I've failed, and and I'm going to be depressed about it. I don't know. Maybe some people work it that way, but I certainly don't. It's very important for me, and I think for all mathematicians, to meet with, other mathematicians and learn about, areas of mathematics that you didn't know about, or even area of mathematics that you did know, but, maybe someone, figured out something, had some new idea, and you want to actually really understand it. In principle, you could say, well, take the person's paper and read it. You can do that, but that's much more time consuming. Right? It's much, much more efficient to talk with someone in person and have an explanation on the blackboard. I guess you can kind of transmit knowledge because it's a back and forth, right? And so then the person can adapt to what you know already, what you don't know, and you can kind of focus on the bits you didn't know about, right? And then you can really try to, focus on the main core of their argument, which you hadn't thought of, right? And whereas the article, has to address like everybody simultaneously, and so you have to give every detail, and so it's more difficult. Like if it's really in your area, then you can, of course, read articles relatively quickly and sort of find relatively quickly the part that's interesting for you. But if it's not really your area, then that's much, much harder. So then it's really difficult. And so then sort of discussing with a person on the board is a much, much, much more efficient way of kind of transmitting knowledge. I think it's very important to transmit your knowledge to students. Simply, in some sense, that's what we're here for, right? Like if you just understand something in your corner and you don't actually explain it to anybody else, then, maybe you get some personal gratification out of it. But, what's the point? There's a point for yourself, but basically for nobody else then. And so, yes, I think it's very important to kind of, if you think you've understood something interesting, then I think it's important to actually explain that to other people as well. Nowadays, there is really much more of a sort of worldwide mathematics community, which doesn't split. Right? So even in the Cold War, there was more of a split. Right? So there was somehow Russian mathematics, which was very developed, but which was somewhat in parallel to Western mathematics. And there were, of course, contacts between the two, but still a lot of maybe Russian mathematics was originally written in Russian and it had to be translated. And so the communication was not as instantaneous as it is now. And, there were results that were discovered independently on both sides. I think nowadays I don't have the impression, different countries still do have somewhat different mathematical cultures, but my impression is that it's more of a taste, right, rather than different ways of thinking. Right? It's more like different types of mathematics that are more popular in different countries, so people have a different taste for what kind of problems they consider interesting or what type of mathematics they consider interesting. But yeah, I don't really have the impression that there are, fundamentally different ways of thinking about the same problem, because the communication is so instantaneous, everybody has somehow read more, if you're in the same area, you have kind of read the same papers, whatever country you're from. And yeah, so I guess to get math out of my mind, I read books. We like to go on hikes or cook. So I do like cooking, and I don't think I follow recipes exactly. But I don't think that that's what you do as a mathematician either. So it's, so the proofs are rigorous, so you have to write the proof in a certain way so that it is convincing, if you want, for your fellow mathematicians who would agree that this is a complete proof. But the way you come up with it is not, right? So somehow, intuition plays a big role, and you don't, like the way you think about problems, that it's much more by feel, right? And it's just that then you try to make that precise, and then you see if it works out or not, right? But the way you actually, come up with a proof also, it's not by deductive reasoning, right? So the deductive reasoning is only at the writing up stage. So in that sense, if you take the analogy with cooking, the mathematicians are not, the sort of people who would take the recipe and then follow step by step. It's rather the other way around. You would, take 5 recipes for that thing, try to figure out what's the common bit, and then once you've understand that, then you can improvise, and then you can, cook variations of that dish, or, depending on what kind of ingredients you have at home, you can kind of figure out whether it would actually work to do some kind of variation of that dish or not. I guess, in some sense, studying math is really a bit like looking behind the scenes and understanding how the world functions.